Hello everyone. Uh, I welcome you to the day 16 of the training. Till now, we have discussed many things starting from FPGA development, architecture, understanding IDEs, EDA development tools, what is the architecture or the history of the FPGA, and then coming to the development flow in the FPGA designs and understood the difference between ASIC FPGA and the flow between the ASIC chip design in the industry flow and also the flow of FPGA development through IDEs like Xilinx, Vivado, and all these things. In the same way, we got introduced to the Verilog HDL programming for the hardware description that helps us to develop the architecture of the design on the FPGA boards or the hardware that we are looking for on a chip, which is field programmable gate array again. So the advantage of Verilog HDL is we can have test bench simulation in an easy way, and we can also develop the structure in different methodologies. Like if you have gate level modeling, you can take the examples of logic circuits. If you know the connections and circuit design, like schematics of the design, then you can write the gate level modeling. In the same way, we have a feasibility of knowing the behavior of the code and then writing behavioral modeling. So as we know that we have discussed data flow modeling and gate level modeling, today we are moving towards uh, behavioral modeling. So let's go to the today's agenda. Today we are going to discuss about loops in the process of behavioral modeling and some examples that you can understand behavioral modeling. So let's go to the examples, because when we apply what we learn, that's what industry is also looking for practical experience. What hands-on experience you have, that's what it is looking. In the ongoing class, I will try to explain some industrial applications, or will give some tips and tricks of the interview preparations, and also you can make your own set of interview questions and research on the interview questions outside this training in the different blogs or different websites that they have written examples for. And I can show you some of the references in the upcoming classes as well for interview preparations or interview questions. So now, coming to the behavioral modeling, we have synthesizable loops and non-synthesizable loops. We'll come to the non-synthesizable loops in a little bit of a time. Coming to the synthesizable loop statements, we can see if, else, and case. Synthesizable. Why did I call synthesizable? Because whatever you write in the loop statements, those loops will be converted, or the statements that are written in the loops, conditions or any other operations written in the statements will be turned into the hardware description. So whatever lines that are to be convertible in the hardware description are called synthesizable. Hence, in the entire Verilog HDL, we can see synthesizable loops are if, else, and case. Mostly we use both of them in a mixed way, but I'll give you some examples where you can understand, okay, we can implement the design through using if, else, and case. So going to the next slide, you can see. Okay, you can see this is if else loop, and that for that you need to follow the syntax for everything that you understand in Verilog HDL. Understand this, that it has some set of rules or set of syntax that is to be written in this way, where you can implement the design through the particular set of rules and conditions. So that is nothing but syntax. For any language that you learn or that you want to implement in the designs or in the projects, that language has itself a syntax. And I want to remind you again, in the Verilog HDL, the syntax will be very familiar to the C programming, normal C programming. So that is the reason some of the candidates outside and some industrial experts will say, if you can understand C language, you will be understanding Verilog HDL very well for the chip design or for the RTL engineering. Because at the beginning of the C programming, that's the only language that has been developed on the basis of machine level language. That's nothing but assembly language. So I don't want to go to the history of C programming, but it is the industrial standard, like we follow IEEE. That's the standard programming language, and it's way older than any other language. And from there, we have developed all these other languages according to our convenience. Nowadays, some other engineers or some other freelance or any other software engineers, they were keen to develop any new language, like JavaScript is the new one in the mid 2015 or 2014s, and we also know Python from very long. But again, everything has its own syntax. In the same way, Verilog HDL, if you can understand C programming, you will be understanding Verilog HDL. But if you understand Verilog HDL, you can compare yourself to the C programming examples. Every engineer here and there in industry, if you want to enter into the industry, make a note: embedded C programming, Linux, and also um, one other thing, projects are very important, and if you know Python, that will be very helpful. So these are the essential skills. And if in the VLSI or chip design industry, you can also in the embedded domain, if you are going for FPGA design engineers, they are looking for Verilog HDL and also for the system Verilog applications. Remember guys, whatever theory you learn or whatever programs you attend and learn, that's not the ultimate part. It's about how many programming projects that you have written, how many applications that you have made, what is your hands-on experience in the overall years. So that's what they are looking. And if you are in graduation, it will be a lucky time if you get serious on this making projects. Do some projects, apply this Verilog HTL or C programming or embedded C programming into the projects, study about the projects. There are many freelancers, many sources in YouTube or in the websites or in some internship companies where they can provide you enough knowledge, trainings, and also the projects portfolio. So build the projects. That's where you stand among the crowd. And interview shouldn't be like a exam preparation. Whatever you learn, you shouldn't be reading about that. Whatever you learn, you implement, and you should be able to talk to the interviewer about what you have learned. I'll repeat this in the later classes as well. Let's focus on the today's behavioral modeling with if else loops. So in the if else loops syntax, that is the syntax: if condition, begin and end the statements, and else begin and end the statement. If a is equal to b, go through this condition. Else means a not equal to b. If true, else false. Or if false, if a not equal to b, this is the condition. Else, if else means the other than this if condition. So else a equal to b. So module 4x1 multiplexer implementation, we have written this code in the earlier sections as well. I want to repeat that because it will be familiar to you to write these combinational logic circuit examples and sequential logic circuit examples. So I'll be dealing with these examples in the later section as well. Come to the module 4x1 multiplexer. As I have said, entire Verilog HTL, you need to be deciding on what type of parts you need to write. Every time it is very familiar. First part is to write module. You need to declare the module mux 4x1 and ABCD SOS1 Y, and second one is input, and input and output is the second part. Third one is registers and wires. Fourth one is assign. Fifth one is always. So from here the actual procedure begins. So that's the reason it is called procedural blocks. And in some cases we also start from initial begin, so that we are setting some standard, some defined function for the entire Verilog HDL or for the hardware description. So it should start from, for example, in the design, if you want to start from initial clock begin from 1 high or clock high, so then you need to start from initial begin clock high and then always at the rate of inputs or always at the rate of positive edge clock. So when did this procedure begin? Only when those were inputs or at the positive edge of the clock or negative edge of the clock, negative edge of the clock. Negative means negative. You will see the examples. And positive edge of the reset, negative edge of the reset. So begin if, else and end module. This is what Verilog HDL for a 4x1 multiplexer looks like. And then I want to repeat one last time. So once you write the declaration of module, it is better to write end module again for this module itself. Nowhere else in the entire Verilog HDL you will be writing Verilog. So you write module, write end module. That's where you won't forget this end module, and you will not be figuring out what mistake you made in the debugging stage in the design. Okay, we will get to the end module and we'll check whether end module is there or not, but sometimes it is better to practice a particular block kind of developing the design. For example, I myself want to explain you part wise. Part is nothing but module, and end module is the same part, and I'll give you some examples. Input and output is the second part. As imagine it is a block, second block. Third block is about registers and wires. Fourth one is about assign. Fifth one, actual process begins always, and begin the process with ending on it. When you begin, you need to write end. Same, this is another block inside the always procedure. Always at the rate inputs, inputs, or at the rate positive edge of the clock. So all these things were depending on the S0 and S1. That's the reason always at the rate of change of S0 and S1 you need to be selecting on this. So then if S is equal to 2-bit 00, you can directly write 00, but as it is a binary value, you can't represent standalone 00. It will be considered as decimal, but 2-bit binary 00 will be looking like y is equal to a. And then for the selection, I mean multiplexer selections, I will be telling you. Here you can see the best example with if else and case. I'll explain both, but understand how to write if else. Just follow the condition. If condition and y is equal to a is nothing but a statement. If there is one statement, you don't need to write begin and end. If there are two statements, you will be writing begin and end between the statements. So I will give you that repetition as well. Just understand, this is the procedure you are writing since we introduced Verilog HDL. So if, else if, and else, that's what you need to continue. So for every condition, and how this will be executed, it will check for the inputs and outputs and registers and wires. Done. So and so, and now you got selection input as 0 and 0. Then it will be going to 0 0. Then A is selected and it comes out of the loop and ends the module. That's it, done. Now if you give 1 0, S0 and S1 as 1 0, then what? So it comes to this point, and if S0 and S1 are 1 0, then you will be getting a selection of y is equal to C. Don't get confused with S0 and S1 alignment. It should be how you have declared. If you write S1 and S0, then this 0 will be representing S1 and this 0 will be representing S0. Then there will be some confusion between getting the output B and C depending on the S1 and S0. As we all know, it should be like very basic. S0 and S1 stands in this way. Don't get confused. If you get confused, come talk to me. I will be explaining all these things. Then come to the behavioral modeling. Syntax. Another example in behavioral modeling. Everything will be in behavioral modeling from today. And for the next 3 days of training, mostly I'll try to have this behavioral modeling examples until you get a hook of it. Like, you need to understand the usage of behavioral modeling and what we do in the industrial standard. How do we need to apply for a project? That I'm going to give you a project at the end of the training. I might give you more than one project, but yeah, till now we have done 4 projects, and from this we are doing with example projects with example codes of each combinational and sequential logic circuits. But understanding of these cells, combinational logic cells or sequential logic cells, will lead you to the major project, which has a combination of all these blocks. I have made you implement those things as well. In the same way, we will be discussing the ultimate projects, which will involve the entire knowledge what you have been learning now. So yeah, this is the syntax usually case when you use the case loop, case statements. We call it as case statements. When you use case statements in the procedural block, always in the always block, now you are using if else, you will be using case. So when you use, you can mention some condition of the case. I have written case 1, but it can be of 3-bit binary 00 0, 4-bit binary 0010. So in that way you can write this, and you will be understanding in the examples. When you write these examples in EDA playground, then you will be understanding, okay, there will be no syntax errors, and you will actually practice in EDA playground. And I will try to give you a hands-on experience video on EDA playground as well. So case 1, 2 and 3 and 4. So begin, multiple statements and end by default. So once you give the expression of the case, okay, what variable you are working with. For example, we are working with register S here. So case S, and then S1 and S0, S0 and S1, S0 and S1 you will be using in here. And then default, you need to say S is equal to 0. The selection inputs are 0 by default. So if this is not the condition, it will start from the cases again. So that is the loop again. So end case, whatever you begin, you need to end. So begin, end case, but with a default. So you will understand with a better example. So come to the 4x1 multiplexer again. By implementing if and by implementing case, what is the major difference? Why do we need to use case, and why don't we use if with the easy of understanding? Okay, it is easy to use for us, but in the lines of code, the implementation will have some slighter delay than the case statements implementation in the hardware description. So what do you prefer? A circuit which has more delay in a sequence, or a circuit which has a parallel execution in the hardware description? So you need to note down a point here. Major difference is here if else will be executed on each condition. So if this condition is executed, done. If it will be checking with all these 3 and it will be going out. So but the description, hardware description, will be written in that way such that for each selection input there should be some hardware. So it will be taken in this way, in a loop in a particular implementation of a hardware in a sequence in the levels, as we have discussed. A level 1, 4 level, 3 level, 2 level, it will come in the levels wise when you apply from left to right in the hardware. So begin and end, if else will be implemented in a sequence, but in the case, whatever case you take, it will be implemented parallelly executed. And then coming to the each selection, for example, you will be declaring module declaration, input and outputs are declared perfectly. And register, you need to declare wires as well. Why did I take 1-bit 0? It is nothing but 2-bit selection of a wire. This is a register, I mean wire. So for that wire, this is one wire S, and it has 2 bits S0 and S1. So that are represented S0 and S1, S0 and S1, S0 and S1, S0 S1. Follow along with my mouse cursor and you will be understanding good points. So whenever it is 0 0, you will get A. Go to the truth table. If you get confused somewhere while writing the Verilog HDL code, it is okay. It is completely normal to take the truth table or take the Boolean equation or take the logic circuit. With multiplexer logic circuit, you won't be able to write the Verilog HDL code in this way. But if you have the truth table for the behavioral modeling, if you have truth table, you can write a good understanding of these case statements or if else statement. Take the truth table, keep it aside and implement. I will be implementing with the truth table in the next examples as well. Follow along. So assign, you need to assign because we have declared S is 2-bit, but what are there in S? You need to tell the hardware description that or EDA tool that S is having S1 and S0, then S0 and S1. So coming to this implementation case, here I have written case 1. I have already said you will be writing 2-bit binary 0 0. 2 is the size, B is the radix, 0 0 is the value. So what value? S0 and S1 value, case S. So this S will be represented along these cases. All these statements are each individual case. If this is the case, follow this answer. If this is the case, follow this answer. Answer means follow this step. This is the output. So what we are setting up here? We are setting up a relation between output and input. Output will be in the LHS like this and input will be in the RHS. Between the relation, you can say if 2-bit binary 0 0, forget about multiplexer. I am giving a general example of the case statement, one single case statement. If S0 and S1, two variables A and B or X and Y, 2-bit binary 0 0, if this is the case, understand in a human language, if this is the case, output should be AND operation or operation between A and B. Sorry guys, my computer is low. That's the reason I'm not writing on the screen. It might be difficult to understand, but I'll try to implement with the design. Okay, I'll make it up to you. So if this is the case, you can understand output is equal to input. Now we have set a relation between output and input. Every time you understand the Verilog HDL implementations with case statements, that you will be getting an understanding with 2-bit binary 0 0 and output is equal to input. Our output will be related to input. So this can be LHS and RHS. I am sure guys, since childhood I've been making this LHS and RHS in the mathematics. Hell of a job. Okay, so in this way we write case statement and colon is must, that is the syntax rule, and semicolon is also must. So if you forget one of these, entire program will be ruined. And default, why did I keep a default? Default is declaring about output here. We need to set some output. If there is no selection of any input, what is the output? Y. You can write it can be of 0 or you can write 1-bit binary 0, or if you are not caring anything about what is the output by default, you can write 1-bit X, don't care. So 1-bit high impedance. High impedance is nothing but 1-bit Z is nothing but open circuit. So this will be open. It's not connected. Y port is open. So it has no value that is going through that. Until you get a selection high, then Y is enabled. So it is not to be writing this open circuit if this multiplexer is connected to some AND gate or some logic circuit or some other multiplexer. If you break the circuit with open circuit, there will be some design issues. So it is not ideal to write that. Now we are discussing only multiplexer, but in general, if this is the case, if I write open circuit here, what happens? Circuit gets break, and in the design there will be a bigger flaw. That is the major reason you need to be taking care in the industry while you are implementing group of designs. So Yeah, coming to the next topic, non-synthesizable loop statements. Here we can see most of these are in C programming. Structure is the same. You can go with the same syntax as well. While loop, repeat, and forever loop. Repeat and forever loop are very friendly enough. You can understand with a click of a second. Just let us go through the syntax. For loop syntax, you need to initial begin. Whenever you want to start a loop, initial begin. It is better to write here as well, initial begin. But in the always, you can't write a initial block. In the procedure block, you can't write an initial block. Initial block should be a separate thing. Now you are writing initial begin, so then you begin with the for loop. What is for loop syntax? For example, you can take I is equal to 0. This step is nothing but initialization. Okay, initialization. This step is nothing but process. And then this is increment. How many times it should be incremented for loop, or this can be execution as well, or simply condition, you can say. So what do we have in for loop? We have three things: initialize, condition, increment. This is initialization. Loop should start from beginning, start from one point. That starting point is nothing but initialization, and it should have some condition. What is that condition? Whether it should have some ultimate step, the ending step it should have, and what should be the functionality of the loop. It should increment or it should decrement. We have two most favorite things in the for loop that we implement: either we increment or decrement. And then output, dollar display. Don't worry about dollar display, I will be explaining in the upcoming classes. These are some of the system tasks where these are predefined functions. So yeah, count is equal to percentage. In the semicolon, I mean in the quotes, you can write whatever message you want to display. For example, everyone would have written hello world here, right? Hello world. In the same way, we are writing count is equal to, we want to count this thing. And if you want to add some time as well, you can write dollar time. Got it? So this percentage d will be interlinked with the variable count. Whatever count is happening, that is written here. And if you take I less than 10 and I plus plus, if that is the case, mostly you can you might have seen this I implementation, and that I can be count, and you can take, instead of count, you can write I. Count is equal to percentage d and I, whatever values you have, I. And now what is happening here? It starts from 0 and it will check the condition. If it is 10, okay, 0 is less than 10, yeah, 10. So count plus plus, then what happens? It will be incremented, like incremented by +1. Plus plus is nothing but incremented by 1. And now 1 happened, and then 0 will be displayed and 1 will be displayed. Now 1 will be checked again in the loop. Okay, now count is equal to 1. 1 is less than 10. Okay, then increment. Now it is 2. It is again incremented. It is taken to 3. So again implemented 4. So this way loop executes until it gets to the 10. Okay, 10 is not less than 10. Loop exits at 9 before stage. Increment, not increment, and end. Loop will be ended. That's how loop works. And while loop, you can see the syntax. It is a bit convenient than for loop, but for loop is the most simply executed if you understand the for loop execution. Okay guys, then for loop, for while loop, initial begin and end So in the initial begin, count is equal to 0. Forget about this semicolon, you need to keep semicolon here. And while count is less than 10, begin display count plus 1. So this is the condition. Same, you will be seeing all these three all the time. Condition, initial value, and function or increment. All these three are available in for loop as well, but in a different syntax. Understand this syntax. Why did I take count example? Because it is easy to explain and it is easy to understand in the beginning itself. Don't get overwhelmed with this all these things. Yeah, this is the while loop syntax. And coming to the repeat, just instead of while you can have repeat condition. Repeat how many times? You need to tell repeat how many times, and initial and increment. So repeat is bit easy than while loop. You need to write the condition, but repeat. Okay, repeat for 10 times until the 10th time. Repeat the 10 times. It will repeat for 0 to 9. Yes, 0 to 9 you have 10 values. And if you say repeat 11 times, then it will go for another step 10. And display count is equal to percentage d and count is equal to count plus 1, same increment. So everything has initial value, condition statement, and then increment. Don't forget this. Forever loop. Okay, and for this you need to look for clock generation. It is mostly used for only clock generation, and the clock should be initially 0 as we consider in the hardware descriptions. And forever after 10 nanoseconds, this is after 10 nanoseconds, you need to declare forever. After 10 nanoseconds, clock is not equal to clock. So the clock begins and end the clock, and clock signal is generated with t is equal to 20 nanoseconds. Why t is equal to 20 nanoseconds? For every for 10 nanoseconds, and initially before 10 nanoseconds there the clock is 0, and after 10 nanoseconds it is high. Then I mean till here it is 0, right? Now we have said 0 not equal to 0, then I mean clock not equal to initial clock. So what is the new clock here? Negation of 0, it is nothing but 1. So the clock is 1 when after 10 nanoseconds. So again after 10 nanoseconds it will go to the low. What happens then? 0 to 1 and 1 to 0. So again it will go for another 10 nanoseconds. So it is repeating. So then the period is 20 nanoseconds. 0, 10 and 20. So 20 nanoseconds. That is how you can write forever loop for the clock cases. So coming to the examples, now you will have a bunch of examples from here and all, from the behavioral modeling, and also only in the behavioral modeling. I will not be repeating data flow or gate level modeling because we don't use them very familiarly in the industry. Now we are only using the behavioral modeling of the hardware description. So take the 8x1 mux multiplexer as you have written for the 4x1 multiplexer. You can write for 8x1 multiplexer. But before you start writing this 8x1 multiplexer, have this truth table with you. From this, you need to write, okay, 8x1 multiplexer. What do you have? You have one output and 7 inputs. That's what 8 inputs. 8 inputs and one output. Then you have 3 selection inputs as well. 3 selections inputs, right? Now how many? 8 plus 3, 11 inputs. You need to write all these 11 inputs, then one output. Got it? Hence, in the same way, you will be writing input and output, wires and registers, always block and begin with the begin with the end and case with the end case and with the default and end module. Case implementation. Why do I explain only case implementation? Till now we have used if else, but now case implementation will be very easy and it's a parallel execution. So whenever you have this 110, okay, now 110, what is the, what type of selection? You can write S2 and S1 S0 also, but 0111, what is the output you are declaring? You need to declare 110. What is the output? It will be taken as G. So most significant bit will be on the right and less significant bit will be on the right, on the left. So you can also write from S0 and S1 and S2. So now you know about S0, S1 and S2. Why don't you implement this design and come back to me with that answer, and then let me know what you will be getting for 110. I'll give you a hint, I'll give you the answer as well. For 110, if s is equal to 0 and s is equal to 1 and s 2, and if you are considering in this truth table in this way, and then you will be getting 0, you need to count from this way, 0 1 1 1. So 0 1 1 1, D will be the answer. But as we all know, however you write these case statements, you need to declare them in this way in the truth table as well. So don't get confused. Based on the truth table you get, write this flow, no confusions. Then you can write 0 0 3 bit, as it is 3 bit you can write 0 1 0 0 1 1 1 0 0 1 0 1, all these selection inputs, and based on that, if it is 7, you will be getting H. It is 1 1 1 selection input, and it is 0 0 0 selection input, A and H. In the same way, whatever input you get, if it is 0 0 0, A input will be enabled to the Y, and you will get the output whatever data you have. For example, 1 0 1 1 0, that data will be sent to the output, and output has 1 0 1 1 0. Okay, so that's it. And then coming to the 2 by 1 multiplexer, module mux 2 by 1 A comma B comma S comma Y. So that's how you can implement this with the AND gate as well. With the multiplexers you can implement whatever logic circuit you want to implement, and then for that, with the use of 2 by 1 multiplexer, you can get the AND gate application. Think about this way, and if you connect the S with the A, and for this Boolean equation you will be getting AB. And what about S bar and A bar dot A is nothing but 1, so you can ignore that. And then A dot B, you can have AND gate with you from multiplexer 2 by 1. How do you implement? Assign statement, and this is a ternary operator. If S is equal to 1, you will be having, and if S is equal to 0, select A input. That's what we are declaring now. Okay, so yeah, that's it. I think you can see the AND gate using multiplexer. Why do we implement AND gate with multiplexers? Because in the logic cell implementation of the designs, it will be easier when you have these logic cells removed and replace them with the familiar circuits like multiplexers, which have lesser delay or which have advantage in the hardware description. So module AND gate, A comma B comma Y, input and output, you are instantiating multiplexer here. Whatever the pattern you write, that should be enabled here. Now we have considered S is equal to A. Hence, you don't need to write here. So A will be taken here. That's how you can write in this way. So then let's go to the next example. It is a full adder implementation. But before full adder implementation, understand this is the full adder circuit. What are the inputs? What are the outputs? You should be familiar with. So A is one input, B is another input. You can add X and Y also, and you can have carry input, sum output, and carry out output. So the truth table, I'll try to give you a truth table, but sorry, I didn't implement. But full adder implementation truth table I will give you. If it is a 4-bit or 3-bit full adder, I will give you example. If you can no, not to confuse you now, I'll give you the example of full adder truth table as well. But understand, you have A and B, C in, sum and carry out. So whenever these three, A and B, I will give you some example in the truth table wise. But understand, based on the inputs A, B and C in 0, 0, 0, if you add them, and what you will be getting, sum is 0 and carry is 0, output carry. And where you get to the 1, 1, 1, the sum will be 1 and carry out will be 0. I mean carry out will also be 1, I think. Yeah, sorry, some syntax error. So carry out will also be 1. In the same way, if you take 1, 1, 0, you can see sum is equal to 1, sum is equal to 0 and carry out is equal to 1. 1, 1 addition is 0 but carry 1. That's how you implement the sum and carry. And how did you write? Module declaration, input and output, wires and registers. All inputs are wires, all outputs are registers, and you have output. I have repeated it. You can ignore this output, and then always you can start from the inputs, then begin the case statements with the begin and end. This begin and end are connected, and every case you are writing begin and end. Why do you write begin and end here after a case statement? Because you have two statements inside a case statement. Like sum is equal to 0 is one statement, carry out is equal to 0 is one statement. You need to have a begin and end for declaring that okay, more than one statement is present in one case. Then here ends the blockage. It won't be related to the next thing. That is how we stop the blockage with the begin and end, and begin and end in everything. Once you write till here, you can copy paste for the next set of outputs. But by default, begin and end, sum and carry will be 0. These values will be 0 in the ideal state, in the default state. Then end the case and module. That's how you will be writing the full adder implementation. I'll give you some time to take a screenshot or write this in your own time and apply it in the EDA playground. That's an online compiler and simulation. Now come to the 4-bit full adder implementation. It is 1 bit, 1 bit, 1 bit and 1 bit. So you have 4 bits. In the same way, you can write one full adder and you can repeat for 4 times. But how do we implement 4 full adder implementations? Nothing but what we do is we implement 4-bit full adder implementation with the instantiation. We can implement the instantiation as well in this way. So whatever code you have written for one full bit, this is a one full adder, 1 bit output. This is nothing. 1 is nothing but 1 comma binary 1 value. The value is 1, right? So the value is 1. Okay. So you can implement the one full adder implementation, and you can instantiate all these 4 blocks with the labels FAL1 full adder label 1, full adder label 3, full adder label 4 with the instantiation. I'll explain the instantiation as well. So write a full adder code for one thing and repeat it in the instantiation. So you will use this code for bigger circuit. So this is a bigger circuit now. This is a 4-bit. And why do you want to repeat this entire code for 4 times? It will be bigger enough and it will take some more time to execute. But what if you write full adder implementation once, and if you can use 100 bits for 100 bits, take it for 100-bit calculation. Now in the normal calculator we can have 12-bit. In the same way, you can have 100-bit and then instantiate with 100 labels. For example, FAL 100 label, full adder label 100th one, like full adder label 4. So as you can see, this is the sum. This is one bit. This is a 1-bit full adder implementation. 1 bit. Remember, output is 1 bit full adder implementation. So you get one carry output and also 1-bit sum output. These are not in a single wire. You either consider sum or you either consider carry outs. It is nothing like that. Based on the serial in, serial out, parallel in, parallel out, that's a different scenario for the shift registers. In the same way they will be implemented. But for the bigger circuit, what we do, we are learning instantiation of the smaller circuits. So you take smaller circuit, instantiate into 4 times. How do you instantiate? This is instantiation. So whatever full adder circuit you have taken, right, A, B, C in sum and carry out, remember this and come to this, and you need to mention new labels A, B, C in sum and C out. In the same way, for the first label 1, you can write 0 0 0 as the label. This is the labeling, and first bit, second bit, third bit, 0th bit. As you can remember, this is 0th bit and first bit and second bit and third bit. Now all together you have 4 bits. So in the representation, in the same way for instantiation, for implementation, 4-bit module full adder 4-bit, name this, and now you have to write inputs and outputs. A and B are 4-bit, hence for 4 bits are divided. For example, if A is equal to 1 0 1 0 or 1 0 1 1, so what you will be taking, A 0, I mean 1 0 1 1. This is how it will be considered. So 1 0 1 1 will be added. If B is equal to all ones or 1 1 0 1, make it 1 1 0 1. Okay, I'll mention with other color. So it will be 1 1 0 and 1. Now you understood how these bits are loaded. That, I mean, let us write A is equal to 1 0 1 0. Oh no, sorry. I don't want to confuse you. Blue ink is the B data. Okay, let us write with red. Now A is equal to 1 0 1 1. And what is B now? You have 1 1 again. Arey yaar. Okay, for you all guys. Now B is equal to 1 1 0 1. Write down, and if you try to add them, what will be the output? So that output will be again split into the 4 bits separately, taken out from each adder application. For example, 1 1, what is the full adder implementation of 1 1? Let us say adding plus. So what is the output for 1 1? If a is equal to 1 and b is equal to 1, you don't have you can see carry as well, right? So Cin is equal to, carry will also be there for okay, this comes in this way and this comes in this way. You add them for 1 1, the sum will be 0 and carry will be 1. I mean carry output will be 1. By default, let us take Cin as 0. So carry out is equal to 1. Or if you take carry in is equal to 1, what will be added? It will be added to sum. So sum is equal to 1 and carry is equal to 1. So this is 1 and you need to do the addition as well for this, but we are lagging out of time. But implement this kind of application for I'll do for the second bit as well. If it is 0 and 1, what is the value? Sum is equal to I mean you need to add C out as C in here. You need to add C in as well. So 1 and C in is equal to, for example, A, B and C in now. By default, A is equal to 0, B is equal to 1 and C in is equal to 1. So what will be the value? 0 and 1 1. Sum is equal to 0 and carry out is equal to 1. Simply, not to have too much confusion. Sum is equal to 0 and carry out is equal to 1. So it is 1 0. Guys, you do it for the third and fourth bit. Okay, I'll do. This is the Cin now. Cin is equal to 1 and A is equal to 1 and B is equal to 0. If it is 1 0 and 1, what is the sum? Sum is nothing but 0, carry is equal to 1, C out is equal to 1. So carry out is equal to 1, sum is equal to 0. You can see it is 101, right? So 101, sum is equal to 0, carry out is equal to 1. Sum is equal to 0, carry out is equal to 1. In the same way, for last bit 1 1, and if it is 1 1, 1 carry out is equal to 1. So 1 1 1, what is the sum you have? Sum is equal to 1, carry out is equal to 1. Now consider what is the value here? 1 0 0 1 and 1. So you can consider this way or you can consider this way in some of the applications. So 1 0 0. So this one is from this bit and this 0 is from this bit. This 0 is from this and this is from here and this is from Z out. I mean from this adder output is this one. Output is what we are considering. So this is how full adder 4-bit full adder implementation can be done. And then coming to the 7-segment display, this is very much necessary program, very much needed in the industry. So come to the 7-segment display, understand the design first, then go to the writing of Verilog HDL code. But why do I specify on the hardware? Each one of this is a LED. Okay, I'll remove your confusion. Coming to the another example, this is very important in the hardware description language. That's nothing but 7 segment display. It is one of the key elements in the hardware boards, like you will be seeing in this way. So let us consider this is the 7 segment display. You are coding for this Verilog HDL to enable this application for the outputs. So whatever you see the outputs, that should be displayed in here. For if you are counting 16 hexadecimal values F, F, F and F, uh, that's a 64-bit or 16-bit or 32-bit output you are looking for, you can look after these displays. But how do we design or describe this hardware description in the entire board in this chip? So that's what we are looking now. For this 7 segment display, you can see how these are connected. Whatever Verilog HDL code you give, that will be turned into this entire code. For example, for the selection, for the 4-bit selections, for every binary input that you give, that to be displayed on this value till 16 values, whatever output you get. So for example, if you are having 0, so these LEDs should be blinking on. If you have 1, if you have 2, 3 and 4, 5, 6 in this way, then you have to see only these LEDs and remaining LEDs should be off. So for that, we need to enable this LED by giving the supply, we need to disable the LED for that output. Hence, if we give value 1 to the LED, that LED will be blinking. There will be resistor circuit safeguarding the each diode. This is an LED diode, so there will be some resistor circuit as well that is connected to the each LED. And for this LED to blink, you need to give value high. So now each LED is represented with a bit variable with A, B, C, D, E, F, G. Hence, let us consider the value of 0, and I will also consider the value of 8. So for the value of 8, you need to enable all these LEDs to blink. So then, to blink all the LEDs, what will you be considering? You will be considering all the values of this array. Let us take this as an array. So as a register of vector, this is an array. In this you have it's a 7-bit array. That's the reason 7 segment. So 7-bit array, if each value is 1, then the LED blinks. And if each value is 0, what if? LED is off. This is nothing but the default statement. But what if? What are we considering? So we are considering 8, right? 8 should be taken in terms of binary. What is the value? 1 0 0 0, and that binary value will be represented in A, and for this binary value you need to enable all the A inputs. If we write this case statement, let us understand. First step, I'll write Roman numbers in a flow. Follow these Roman numbers. First step, we want 8 on the display. 8 on the display. We want 8 on the display. Okay. Now let me take. So we want 8 on the display. So this is decimal output that we can see. But what is the decimal value? Binary value of 8? It is A. So for binary value of A, for this case, if this is the case, this is the binary value, then I should represent this output in terms of binary as well. So then I took another register. This is one register. I took another register that I can see all the values will be sitting. So one is input and one I am seeing at output. So G is connected here, F is connected here, E is connected here, D is connected here, B here, C here, and A is connected here. Okay, now whatever the values you give, 1 1 1 1 1 1, for 8 all LEDs should be on, right? Then only it displays as 8. So then all the values of each LED is 1 bit, each LED is 1 bit, then all LEDs have high value. If you are giving 1, the voltage is 5 volts. For example, 0 and 1. 0 is 0 volts and this is 5 volts for each LED. So 1 and 0. What it takes? 1 1 1 and 1 and 1 and 1. All these are ones. So then you will be getting value as 8 displayed. That's how it works. So we need decimals, and the second one is it, what is the binary value we can give in the case statement. This is the second step for the condition, and third step we need to declare, we need to connect this to the output. So this is the third step. Third step is nothing but declaring the output. And what is the fourth step you are seeing? Fourth step, you are verifying all these LEDs are on or not. Check this code. You can see for 0 value, for 0 what should be the value? Except for 0 value, except this LED, all these are represented. So it is A, B, C, D, E, F, and this is G. Now G is off, so G is equal to 0. All these are on, so it is 1. It is 1. This is F. Understood, guys? So if you have A, B, C, D, E, F, G, H values, I think to the G, if you have an array of these LED values, these bits represented, what is the value now? 1 1 1 1 1 1 0. Only G is 0. So remember this, all ones and 0. All ones and 0. You need to understand for each bit in this way. Try to simulate this with the each value. I'll erase all the ink. So 0 1, only if this is A and B and C. Clockwise, you start from here clockwise, and B and C values are high, and remaining all values are 0. So A is 0, G is 0, and F is 0, E is 0, and D is also 0. So all these are zeros, only B and C are 1. A, B, C, B and C are 1, all are 0. Then you get value of 1. In the same way, you can write for all these numbers. Try to understand this in the same way, in the following way: 1, 2, 3, and 4. Okay, so I hope you understood this 7 segment display in this way. So you need to declare the module name, what is the input and output. You have input and output. You need to declare that register here, or you can write output reg here itself. You can declare in any ways, in your convenient way, however you learn. So always at one point, one expression, always at the rate inputs, and then case expression. Okay, a now at the wire input a wire, this is the wire, let us say, and these are the registers. This entire thing is a register. Register can be array, register can be vector as well. So register, simply register. So register, and it has 7 bits, you can see 7 bits. For every case is representing in this format, case value. Whatever case you take, whether it might be S, in the previous examples, case, you have considered case, so this is the concatenation value. Whatever the concatenation value, it will be taken from this. In the same way, you can take the case, here you don't need to concatenate, and you can take the values. All these values are for the A bit, 4 bit A. 4 bit means you have 16 values, 16 values till the hexadecimal F. Got it, guys? So by default 7 bit B00 is nothing but it is, you can take 0 0 0, all 7 bit values. You can have these many zeros. Instead of writing that, you can write this way. Okay, all 7 bits will be of value 0. That's what the explanation is. So these things you need to remember, guys. And as I want to show you all, take this as inputs, pause it here, try to write the A value and B value for each number in the LED. It will be familiar to you. So, and also don't forget to remember the structure. This is the well-known Verilog HDL 7 segment display code for the hardware. This relates to the hardware, how you can implement this Verilog HDL description, and you are influencing the hardware out of it. So that is how you can do all this. So 0 1 2 3 4 5 6 7 8 8, you can see all the LEDs are glowing, and 9. A is nothing but 10, B is 11, C 12, 13, 14 and 15, F is 15. So 0 to 15 you have 16 values. That's 7 segment display. Now coming to the ALU. ALU is nothing but arithmetic logic unit, where you can do bunch of operations like addition, subtraction, multiplication, division, logical shift left, logical shift right, rotate left, rotate right, depending on the value of selection, value of mode of operation that you are looking for. For that you can choose what type of operation that to be done between values. And logical AND operation, logical OR operation, logical XOR operation, logical NOR operation, NAND, XNOR, and comparison of the greater symbol, which is greater. If A is greater than B, then you can take value 1 true, and if it is not greater than, I mean A less than B, it is value 0. So A is equal to B, value all 8 bits or 8 bit decimal, the value is 1. If not equal to B, that is the condition, then 0. A is equal to B, E is equal to 1, then this is selected, and if it is 0, this is selected. So hence, what is the application of ALU? You can have all set of operations which can be executed parallelly. That is a major unit in the entire hardware. So this is one of the key elements in the architecture of any processor. For example, Cortex M0, ARM, any processor, AMD processor, Spartan, Intel processors, ALU is the must to do bunch of operations in this way. So yeah, same declare module in this way. What is, you understand what is the input, what are all the inputs, what is the output, and you have output. So it is y is equal to c out some output carry out flag, and you need to have a temporary variable here for that temporary variable, because whatever operation is done, that is stored in the temporary variable, and at the end, after all the operations is done, the final output will be given to the carry out. So that is how it is done. That is the reason we are assigning this step. This is one familiar step that you should be remembering all the time. But again, come to the module part, first part, and input and outputs, second part, and register and wires, third part, and here you are writing assign values for output and temporary operations value. For y is equal to out, it's a ALU output, and assign temporary variable as binary value 0 and a and b are set to be zeros, binary values. This concatenation is nothing but what are the values available, it is 0 and 0. So C out is the temporary, if the value of temporary 8 bit, I mean whatever decimal bit that they get, after that operation, that will be stored into the carry out flag. So C out, always at the rate, every step, always at the rate star is nothing but at every value of the change, at every value of the a or b input, or simply you can write a comma b comma yes, what are the inputs that you can write at the always stage. Then case begins, whatever the selection uh, that based on the selection, if you want mode of operation, for example, a is the selection input, but s can be deciding factor. If s is equal to some 1000, if that is the selection, then you are selecting AND operation. If s is equal to 1010, you are selecting XOR operation. So that is why we call it as selection input. So also we can see if s is equal to 0010, we are seeing for multiplication selection. So this way we can operate the ALU in the structure. So this is the ALU code that it helps out for the operations, and that's it today. And this is the we have ALU here, and we can also have some IO block that is connected to one of the LEDs, and based on the some output that you get in the LED. So I mean, if you are getting a plus b is equal to 1, so that one should be displayed here. So that one should be displayed here in the connection. So what I'm saying is, if the values, for example, if the values you have enabled a is equal to 1 and b is equal to 0, what is the sum? You can get the sum from 1, ALU from 1 for the ALU operation, and then 1 is got into the 1 bit binary value 1 is sent to the LED circuit, and that one will be displayed here. For example, if you have one here, it will be displayed in this way. So that's how it can be displayed. Hence, that is the major application that we can see of hardware and software. So thank you guys. If you have any questions, just let me know. You can talk to me, and thank you for attending day 16 of the class. See you.